Okay, so typically the sum of internal impulses on a system equals 0. So this means for our impulse momentum formula that we're using, we can eliminate this term, and we end up with the sum of the momentum initially equals the sum of the final momentum. This is called conservation of linear momentum. So let's look at an example associated with this. Let's find the distance that a spring is compressed here in the system over on the left, where we have a 15 kilogram block hooked to this spring in the uncompressed state, has a K value of 10,000 newtons per meter. We have another block that's 10 kilograms coming in from the right at 15 meters per second. We can apply conservation of momentum. We have momentum A times the velocity of A, which is 0, it's just sitting there, plus the momentum of B times the velocity of B, which is 10 times 15. This equals, when they connect and hook together, the sum of the masses, which is 10 plus 15 is 25, times the final velocity. So that velocity is 6 meters per second squared. All right, so we're going to take that velocity and stick it in a conservation of energy equation. So initially we have, for our initial kinetic energy, we have 1/2 times the mass of the combined blocks of 25 times 6 meters per second squared. We have 0 potential energy. The spring isn't squished yet. And in the final situation, when the spring is totally switched, we've lost all velocity. So this first term is 0, and we have 1/2. This should be 10,000 x squared. So now we can solve for x, and x should equal something around the lines of 0.3 meters. Okay, that's conservation of linear momentum. Conservation of linear momentum is often used when collisions occur. And so when can we look at external impulses and assume they are equal to 0 or negligent? So when are external So when are these external impulses equal to 0? When time is short, some of those impulses can be taken as 0, or if the load is really small over a small time. So we call these non-impulsive loads. And they can be eliminated from our analysis. So when do impulses matter? Well, when you have very large short-term forces. For example, a situation where perhaps a bat strikes an incoming ball. At the very short instant where we might be analyzing this, the instantaneous change of direction when this occurs, the weight of the ball can be considered negligible because the time scale is so small, but the force of the bat on the ball, changing the direction of the ball, is very large. We call these impulsive forces. The force of the bat on the ball is an impulsive force. Often these occur due to explosions or striking of one body against another. So let's do this example 15.6. Here we have a 300 kilogram hammer being dropped onto a pile, and it is 0.5 meters away from the pile when it is dropped. We want to figure out what is the impulse this hammer has on the pile. or rather, what is the impulse which the hammer exerts on the pile? That's different from the actual problem, but we'll see that our answer is the same. And let's use momentum to solve this problem. First off, though, we need to find the velocity of the hammer just as it strikes the pile. And we can use conservation of energy to do this. So we have T1 plus V1 equals T2 plus V2. And the hammer starts from rest, so we have T1 0, but we have a potential energy due to height. And then when we strike this thing, we end up with 1/2 the mass of 300 times our velocity squared. And we'll take this as our datum, so we have 0 potential energy. So we end up striking the pile at 3.132 meters per second. So now, what is the impulse the hammer exerts on the pile? So I've drawn the pile over here, and when the hammer hits the pile, we have a velocity here that this is moving down. And so there is an impulse, R, that connects with this pile. The pile also has a weight, and there are also frictional forces here holding the pile up. Let's call this direction positive, that we're heading down. And let's set this up so we've got M1 V1 plus. Now, we only have one impulsive load here, and that is R. The friction and the weight are very small, negligible compared to R over the instantaneous time period, almost instantaneous time period that we are interested in. So we have the integral of R dt equals mass times our velocity 2. Well, in this equation, we know what our mass is. We know what our initial velocity is. It's 0. So this relationship here goes to 0. And over here, we know what our mass is, but we don't know what our velocity is. And of course, we're trying to solve for this. So we have two unknowns here. So we need more information. We essentially need to figure out what the velocity is. So here in our system, we have the hammer has connected with the pile. We have a weight. Let's do it in pink again. Because the weight, again, here in this situation is non-impulsive, we have our friction holding this up. Again, non-impulsive. But then we have here, now this is going to be internally, we have this R facing off against this R, and those are going to end up canceling. Again, we're going to have this V in this direction. So at the instant before impact, we have mass of the hammer, velocity of the hammer, plus mass of the pile, velocity of the pile. And those velocities will both be initial. And then this equals, once they connect, it's mass of the hammer plus mass of the pile, now is one object like I have shown here, times our velocity 2. Again, there's no impulses because, first off, the pink forces are non-impulsive, and the R's cancel each other out. Now, plugging in our numbers, we have 30 kilograms times the mass, the velocity we calculated above of 3.132. That's the hammer, plus 0. The pile has nothing in terms of velocity, so it's initially at rest. Then we have 30 plus 80 300 plus 800, actually, kilograms times the velocity, our final velocity. So here our final velocity turns out to be 0.8542. That's with both of these objects combined now, so the pile is moving down into the soil. We can now take the relationship we set up above, copy, and paste down here. So referring back to this again, so now we have the integral of r dt. This is what we're looking for, our impulse, and this equals the mass of, so let's just do this for just the hammer now. We're just looking at the hammer. So we're looking at this free body diagram, or rather we're going to analyze the pile instead of the hammer like they did in the example. And so with the pile here and the free body diagram associated with this, we see that the integral of r dt equals mass 2 actually. So this is the 800 times our velocity of, that we just calculated above, 0.8542. So that means that this impulse must have been 683 newtons. And that's actually Newton seconds.